In the last video, we discussed line spectra, and shown here is the line spectrum of hydrogen gas. And if we look in this line spectrum, to our eyes, we're going to see four different lines or four different colors. These four lines occur at 410, 434, 486, and 656 nanometers. And these lines are going to be violet, blue, blue-green, and red. And it was kind of fascinating to chemists at the time, and Balmer put together a relationship. But here we see four lines. It's very, very simple. And there was another chemist by the name of Rydberg who was able to put together a mathematical relationship that said 1 over lambda, or 1 over the wavelength, is equal to RH times the quantity 1 over n1 squared minus 1 over n2 squared, where RH equaled 1.096776 times 10 to the 7th inverse meters. So we had this relationship, and we were able to fit this mathematically to this spectrum, but no one really understood what on earth this information was telling us. So this led to the work of someone by the name of Niels Bohr. And what Bohr did was he was the first one to develop a model that correlated known facts. And in 1913, he came up with his theory of the hydrogen atom, or what we refer to now as the Bohr model of the hydrogen atom. And I want to highlight a couple key points of this theory. And what Bohr did is he related the lines of this spectrum to how the electrons orbit a hydrogen atom. The first thing that comes, a corollary that comes from his theory, is that electrons are restricted to certain energy levels which correspond to spherical orbitals about the nucleus. And we're going to designate these with a number n, which we refer to as the principal quantum number. And n is going to equal a whole number integer starting with 1, then 2, then 3, and so on. There's something called the ground state, which has n equal to 1, and that's going to be closest to the nucleus with lowest energy. Okay, so as we increase n, we are going to increase the distance from the nucleus. And as we increase the distance to the nucleus, we're going to increase the energy. So we can set up an expression now where the energy is equal to minus RH, which is our Rydberg constant, times 1 over n squared. The more negative the energy, the more stable. So n equals 1 gives the most negative value. And one of the things that we can say about this is that the lower the energy, the more stable. So the more negative, the lower, that's going to give us our lowest value, which is going to make this the most stable.